Hi guys, welcome to Rationality, Reason, and Reality. I'm Supernova. If you've been following my videos lately, you know that I'm discussing my math theory that 0.9 repeating does not equal 1. Now in the last video I discussed how one can use inductive logic to prove that 0.9 repeating doesn't equal 1. 0.9 repeating squared does not equal 1 or 0.9 repeating. 1 minus 0.9 repeating does not equal 0. 0.9 repeating does not have the properties of 1. And I was kind of hoping that somebody would actually pick up the gauntlet that I threw down and try to demonstrate how, for instance, they square 0.9 repeating to get 1, and I was disappointed. But still, there are proofs that mathematicians have shown to get 1 from 0.9 repeating. And so I said I would take them on, and I'm going to, starting with the algebraic proof. This may be familiar. I demonstrated this in the last video. 1 divided by 3 equals 0.3 repeating. You multiply both sides by 3 and you get 1 equals 0.9 repeating. Now, obviously, I don't have a problem with multiplying 0.3 repeating by 3 and getting 0.9 repeating. In fact, I discussed in the last video how you can do that with inductive logic. If you do it through some other method, please feel free to share, and we'll see if that's something that you use consistently in all such multiplication. But the problem is in the first premise. 1 divided by 3 does not equal 0.3 repeating. How do we know that? Well, one way to test your division is to do it backwards. You multiply the quotient that you got from your division by the dividend, and you should get the first number that you are dividing. 0.3 repeating times 3 ought to equal 1, and it doesn't. It equals 0.9 repeating. But of course, mathematicians believe that 0.9 repeating is 1, so it's not going to be sufficient to leave it there. How can we test this problem? Why don't I believe that this is true? I mean, haven't I done it with paper? Don't I see that it keeps equaling 3 after 3 after 3? Why would I think that it wasn't 0.3 repeating? Well, because it has a remainder. And if you don't know what I'm talking about when I mention a remainder, let me discuss it with a few simpler division problems, and then we'll get back to this one. Now, a remainder is a concept that you probably learned about when you first learned division in school. And then your teachers taught you about how to figure out decimals, and they just pushed past the remainder, and you've probably forgotten all about it. But it wasn't wrong math. It was just a simpler way to do math, and it seems to work better for our purposes because it's a way of checking your problem no matter what the length of the decimal that you would get in your division is. So if we had a problem like 10 divided by 4, when you first learned how to do this problem, your answer wasn't 2.5, it was 2 with a remainder of 2. And your teacher may have asked you to check your work by doing the multiplication and then adding your remainder. So in this instance, you'd multiply 4 by 2 to get 8, and then you would add the remainder of 2 to get 10. And then you would know that, yes, your answer of 2 with the remainder of 2 was correct. Now you could go on to continue to divide that 2 by 4, and then you get 0.5, but you don't have to. You can cut this off arbitrarily anywhere you want in the problem, and you will find that this works in any division problem. I'm not cherry picking my examples. I'm going to give you one more simple one that just goes on in 3 decimal places because I feel it's sufficient enough to prove my point. How about 1 divided by 8? Now, if you divide 1 by 8, you'll find that 8 goes in 0 times, and you will drop a remainder of 1. So if you check the math at that point, 0 times 8 is 0, and then you add your remainder of 1, you get 1, which is what you were originally dividing in the first place. So you've done the math correct so far. Now, after you drop that remainder of 1, you can add a 0 to it because there is a 0, 1 point infinite zeros that you're dropping from the number that you're dividing. So you have 10, and 8 goes into it 1 time. Now, of course, you know that your answer is going to be 0.1 because now you're doing it after you've dropped a 0 from the decimal place. And the same thing is going to happen to your remainder. That 2 that drops from 10 minus 8 is going to also be 0.2. So if you check your math at this point, 0.1 times 8 is 0.8. You add your remainder of 0.2 and you get 1. So you've done the problem correct so far. Now if you drop another 0 from your 1 point infinite zeros, and you'll find that you have 20 and you're dividing that by 8. 8 goes in 2 times and drops a remainder of 4. Now in this case it's 0.04 because it's been carried 2 times. So your answer so far is 0.12 with a remainder of 0.04. If you multiply 8 by 0.12, you get 0.96. You add your remainder of 0.04 and you get 1. So you've done the division correctly so far. And then 4, after it gets to 0, does divide evenly by 8 5 times, and so your final answer is 0.125, and that, if you multiply it by 8, gives you 1 exactly, and your remainder is 0, and adding 0, you still have 1. Now, this also applies to infinite problems. If it works with any finite number, please try this at home, it works with any finite number, it ought to work with infinite numbers too. There's no reason why it shouldn't. We're not making cases of special pleading saying that infinitely long numbers follow different rules. They don't, especially since along the way when we test this, it is a finite number. So if you divide 1 by 3, first of all, 3 goes into 1 0 times and drops a remainder of 1. And so 0 times 3 is 0 plus 1 is 1. If you add a 0 to that 1 and then divide it by 3, you get 3 with a remainder of 0.1. So if you check your math at this point, multiply that 0.3 by 3 and then add your remainder of 0.1, you get 1. It's kind of important to remember that there is a remainder there, because if you ignore it, you're going to get 0.9 equals 1. You don't believe that's true. I don't believe that's true. You can't forget the remainder. When we carry on to the second place, you'll find that 3 goes into 10 3 times, and you've got a remainder at this point of 0.01. If you do the math in reverse, 3 times 0.33 equals 0.99 plus your remainder of 0.01 equals 1 exactly. This is doing the problem exactly and not rounding off. If you carry it over 3 places, you get 0.333 with a remainder of 0.001. And if you multiply that by 3 and then add your remainder, you get 1. I hope I've made my point at this juncture, because it's so easy to follow along with. If you continue to do this problem, you'll see that through inductive logic, even though we keep adding 3's at every step of the way, we're also adding another 0 in front of the remainder. It's going to continue to be infinite zeros 1 eventually. When you get to infinite 3's, you're going to have infinite zeros and then a 1. And that is why 1 divided by 3 does not equal 0.3 repeating. It almost equals 0.3 repeating. You have to add that remainder, which is exactly what we would expect it to be. When I say that 1 minus 0.9 repeating equals infinite zeros 1, I'm saying that the difference between those two numbers is infinite zeros 1. This math has so far been consistent. You see that the difference is still what we would expect it to be. Now, if you believe that infinite zeros 1 isn't a number that you can deal with and you just want to treat it like 0, you're rounding. That is a rounding error. And you can just take out these equal signs and put in an almost equal sign. And I agree, 1 almost equals 0.9 repeating. 1 equals 0.9 repeating if you're rounding off. I don't think I was ever attacking that argument. I agree that 0.9 repeating almost equals 1 if you round it off. If you round it off, you have to acknowledge that you're doing so. If you are using inductive logic. You can't cherry pick. You can't say, well, yes, I see a pattern that 0.3 keeps repeating. You also have to keep in mind that there is a remainder that's getting smaller and smaller. It never gets to 0. Now, you might think that it gets to 0 if you use calculus methods. It's approaching the limit of 0, in which case tune in for my next video where I'm going to tackle this idea of calculus and limits. I hope you enjoyed this video. Please, I do welcome your comments even when I disagree with them. If you are going to comment on this, I would ask you to please tell me how you get 0.9 repeating from 0.3 repeating times 3. If you're not using the inductive method, I'd love to know exactly what method you are using so I can show you an example that you're not going to use your math consistently on. Because I've thought of this. I know a few other methods and they don't work consistently. And also, I do appreciate you listening, especially when you don't agree with me. I know how hard it is to listen to somebody that you disagree with. So I appreciate that. Subscribe, tune into my next video, and I will catch you later. Peace.